Welcome to this Math Talk Friday. So today I'm going to talk about this IMO shortlisted problem from year 2019, number theory problem 6. It was proposed by Rodrigo Sanchez Angelo, who was from Brazil, if not mistaken. So one reason that want to talk about this problem is, first of all, I already presented this problem to the Malaysian IMO team before they flew to Norway. So which means that I already have the materials, so it makes it easier to present right now. And second is that this problem, I do think that it's pretty cool. And finally, it's Friday night, and who works on Friday night, right? So yeah, let's jump to the problem statement. Now consider this set H, which is the floor function of the set of the floor function of all the integer multiples of square root 2. So meaning that you have 1, 2, 4, 5, 7, skipping 3, 6, and 10, blah, blah, blah. The thing you need to prove is the statement is pretty simple. There is a constant C such that for any subset A of 1, 2, 3 all the way to n, such that the size of A is at least C times square root n, there is small b in A, the capital set A, such that A minus B is in this set H. Now, if you think about it, there are a few ways we can reformulate this problem. So first of all, because everything right now is that they ask for a constant C and ask you to prove something about like constant C square root n, you kind of already know that this problem is it only cares about the asymptotics in terms of n, in terms of n. Sorry, yeah, in terms of n. Another thing to see is that if B is also in this is also a subset, but the condition fails for this one, then the size of B is also bounded above by square root n times some constant, of course. Yet another way to formulate this problem is that if B is any subset of the positive integers, and such that we fix the size of B such that it's, say, equals to k, and also B fails this condition, meaning that for any pair of numbers in B, A minus B is not in H, then the gap between the biggest and the smallest number in B, written over here, is at least in the order of the size B squared. In particular, if the size is k, which we will use it later, then the order will be at least O of k squared. Sorry, not O of k squared. It should be omega of k squared. Okay, so here are the key ideas that I'm going to present. The first one is clever visualization of the problem. So just now, if you see over here, the set H is kind of like, it's discrete and there's some really random skips here and there, which at least for me, it's not really useful. We'll see later how we can translate this into something that is a bit more more uniform and therefore will help us a bit more. The second is custom modulo function. So we probably have already learned that modulo is something that is from integer to integer, and it kind of signifies remainders. Well, nobody says that we cannot extend the definition of modulo function to a bigger set of numbers, right? As long as the definition makes sense and there's no ambiguity, we are free to do so. And third one is the trick on how are we bounding the gap once we already have the first two done. So here we talk. I use this notation of Z, the ring of Z and square root 2. But don't worry about this notation. I'm using here just for fanciness. Maybe if you are already a college student or have already taken some college class, then you might appreciate this a bit more. But this is not really necessary to solve this problem. Okay, so the modulo function we are going to talk about is modulo square root 2, which might be weird because is modulo a non-integer? Okay, now let's do a bit of mental warm-up. So what's so special about square root 2? Like, what are the properties? Well, the first thing that we can think of is it's irrational, it's algebraic. Yeah, we will probably use that somewhere in the solution. What's more important, as it turns out, is the fact that the number square root 2 minus 1 is pretty small. Well, how small is it? How small is considered small? Okay, you'll see this later. Another thing that we want to program ourselves is to ask ourselves, what does it mean to say that an integer d is not in H? So recall that H is this example of H. So let's take an example number 3, which is not in H. So why it is 3 not in H? Because 2 square root 2 is 2 point something, which is less than 2, which is less than 3. But 3 square root 2 is 4 point something, which is already more than 4. So what this means is that for some number c, where if d equals to 3, then c equals to 2, then this in this case c square root 2 is less than d. But c plus 1, the whole thing times square root 2, is more than d plus 1. So if you arrange this whole thing, what you will see is that 0 is less than d minus c square root 2 and this thing is less than or equal to square root 2 minus 1. So now this motivates us to define this what we call as the fractional part modulo square root 2, meaning that f of d. So now let's consider this definition. So f of d is something that is something such that f of d is something that is between 0 and square root 2, and there exists a number c such that f of d equals to d minus c square root 2. So in this case, our c will just be the floor of d divided by square root 2. Now, with this setup, it's a bit clearer how we want to visualize our problem. So what we are given is this set h, some number line, where you skip number 3, number 6, number 10, which is not even that uniform. What if we visualize our problem in this sense instead? So instead of thinking them as integers with some skips, how about we think about it as like integer multiple square root 2. So what we have here, for example, is like 0 square root 2, 2 square root 2, 3 square root 2, and blah blah blah. And in additional, we highlight those parts that are 0 and like square root 2 minus 1 from to the right, that is from each integer multiple of square root 2. So in this case, we will have like 0, 0 to like what, square root 2 minus 1 over here. And then this is like square root 2 to like what, square root 2 plus square root 2 minus 1, and so on and so on. And the reason of us highlighting just this region is, well, because we are interested in the numbers that are whose fractional part is at most square root 2 minus 1. So you can see here that whichever that we highlighted in black, the fractional part is less than or equal to square root 2 minus 1. And whereas those that are not highlighted, the fractional part is more than square root 2 minus 1, but still, of course, less than square root 2. Another thing that we want to program ourselves is that, since we are only interested in the difference of the set, just go all out and just think about like the relatives, or the relative distance between each pair of the numbers in the set B. But how do we do this in a more methodological way? One natural way, well, you can say, is that, okay, let's sort the numbers of B from B1, the smallest, B2 all the way to B sub k, the biggest. And then we consider the difference between the adjacent numbers. So in this case, D of I will be B sub I plus 1 minus B sub I. And why is this attractive? Because if we want to consider things like B sub j minus B sub I, where the gap is more than 1, it turns out that the difference can be written as the sum of the consecutive di's. So D sub I plus 1 all the way to D sub j minus 1. And we already assumed that B sub j minus B sub I is not in H. So what this means is that this number, the fractional part of this sum, okay, there should be a plus over here. Sorry for the typo. The f of this sum has to be less than or equal to square root 2 minus 1. Now let's go back to this to this puzzle. One thing that we might notice is that the what how should I phrase this? One thing you might notice is that the marginal increment, meaning that if you want to go if you want to consider like d sub I to that d sub j minus 1, and then what happens if you add d sub j over here? So one thing that you might see is that if we are at any of the highlighted black part over here, and we add another thing that is less than square root 2 minus 1, or well, something that is really small, there's no way you can jump from this part to another part over here, meaning that you cannot really jump from uh, a, a black part to another black part without a sufficiently big jumps. So here's where my claim where square root 2 minus 1 is small enough comes in. So formally speaking, if c like if f of c1 plus all the way to ci is less than or equal to square root 2 minus 1, and each of the ci's is also less than square root 2 minus 1, then how big can c1 plus all the way to ck be? Well, it turns out that even if you even if you take the sum of the fractional part, not the fractional part of the sum, we are talking about sum of the fractional part, it is bounded above by square root 2 minus 1. So the reasoning, like what I say, like every time you if you start from here, every time you just add something small, square root 2 minus 1, it cannot jump to here, but it cannot be in this in this non-highlighted part either, because otherwise the fractional square root 2 minus 1 thing will be violated once you consider this this partial sum. So it has to be has to always stay in this first highlighted region. And finally, if you want to ask like how small is considered small, well, all we need is 2 times square root 2 minus 1 is less than square root 2. Okay, now I've already talked about the motivation. We still have to turn this into a proper proof. So one thing that is that is evident is that each of them, like f of d sub I, is less than or equal to square root 2 minus 1. Why? Well, just consider the difference b sub I plus 1 minus b sub I. And if our lemma is not true, then this whole thing has to be instead more than square root 2 instead. Why? Because if it's between square root 2 minus 1 and square root 2, then the fractional part of bk, the biggest minus the smallest, will be between square root 2 minus 1 and square root 2, and our number bk minus b, sorry, b sub k minus b sub 1 will be in h, which is a contradiction. So what we could do right now is to say that, okay, if I is the minimum index where this thing, the sum of the fractional part is greater than square root 2, of course we see that I has to be greater than 2, because if the greater or equal to 2, because if I equals to 1, then f of di then it couldn't happen, because f, it has to be less than square root 2, right? So we already know that this one is more than or equal to square root 2, and the last term, f of di, has to be less than square root 2 minus 1. So if you just take off this thing, the remaining one, d1 to di minus 1, has to be more than 1. And yet, by the minimality of I, this is also less than square root 2. So what we do have is that the fractional part of di to di minus 1 is more than 1 and less than square root 2, which is a contradiction, because 1 is less than square root 2 minus 1. Okay, so now that we already have this lemma proven, we want to bound the gap. So before that, let's talk about the intuition. Right now, we have that no matter how the size of b grows, the sum of the fractional part f of d1 plus f of d2 sub 2 all the way to f of d sub k minus 1 is bounded by a constant, and the constant is square root 2 minus 1. So on average, we can say that, yeah, the fractional part is on average is bounded above by 1 over k. Now, our hope is that if we have this fact, then the gap between the biggest b sub k and the smallest b sub 1 is at least on the order of k squared, which means that we kind of want the gap of the adjacent elements to be at least on the order of k. Well, this intuitively makes sense, but how do we show that? Well, it turns out that all we need to do is some clever manipulation of this number f. So recall that f of d there exists that for f of d there exists a number c, where c is an integer such that d minus c square root 2 is greater than 0. And why is this this one has to be greater than 0? Because, well, square root 2 is irrational, so there's no way d minus c square root 2 equals to 0 unless, well, both c and d are 0. And once we consider this factorization, we see that d squared minus 2c squared has to be at least 1. Why? Because this is greater than 0, and this one is also greater than 0, and both d squared and 2c squared are integers. So if we rearrange this whole thing, we get that 2d is greater or equal to 1 divided by f of d. Well, this one is because d is greater than c square root 2. I mean, greater or equal to. So what we want to claim is that the sum d1 plus all the way to dk minus sub k minus 1 is this constant, is at least this constant times k minus 1 squared. So how do we do that? By our previous lemma, we already have that the sum of the functions f, the fractional powers, is at least square root 2 minus 1. And if we rearrange the previous term over here, we do get that f of d 2 times the f of di is greater or equal to 1 over di. So if we just consider these two things and we add everything up, we get that 2 times square root 2 minus 1 is more than the sum of all the reciprocals of the di's, meaning that this one is greater or equal to 1 over d's I minus 1. Sorry, 1 over di, the sum of 1 over di. And basically, this part is just Cauchy-Schwarz. And then you get this k minus 1 squared. So the final result is that the maximum of b minus the minimum of b is greater or equal to 1 divided by 2 square root 2 minus 1, which is basically a constant, times the size of b, which is k minus 1 squared. And as k goes to infinity, the size b minus 1 is kind of like the same as the size of b. So this minus 1 doesn't really matter too much. And therefore, we can say that this is at least the omega of the size of b squared. And with this, our proof is basically complete. Okay, so now let's talk something that is not so Olympiad related, but it's some good extension of like some college math. Okay, so this recall that I talk about this z-type plus square root 2 ring. This is basically all the numbers in the form of like integer plus integer square root 2. And you can show that this is basically algebraic. What's more important are some nice properties over there, which I'm going to unpack soon. So here we can define like the norm. Well, I use this quotation norm because this is not really, it doesn't have the triangle inequality, and this norm can in fact be negative. But anyways, let's define the norm of a plus square root 2 as a squared minus 2b squared. Well, another thing you can show is that this a plus b square root 2 is the choice of a and b are unique for each number in this form. Why? Because square root 2 is irrational. One other thing you can show is that it has the nice property of some norm functions. So in particular here we have like the norm of xy equals the norm of x times the norm of xy. Now one thing that we are interested in is that what happens if, of course here of course here like n the norm is an integer and it's equal to 0 if and only if our thing inside here is 0. But what happens if they are in the form of like plus minus 1? So we say that in this case, like n of x is plus minus 1. Now, there's one theorem which I recall proving this as one of my first year math homework, aka Math 145 from U Waterloo, that all the units are in this form. So like plus minus the power of square root 2 plus 1, where n the power n can be basically any integer, negative or positive. Like for example, if you take n equals to minus 1, then this whole thing is just like square root 2 minus 1. So one thing that why this theorem is special, it's useful, is that if we show that if we use this theorem, then we can show that the bound c square root n in the original formulation of the problem cannot be improved asymptotically. So when I say asymptotically, means that again we don't care about the constant, we only care about like how the like how the bound of the set A, size of the set A grows. So meaning that like we cannot say that oh the statement is still true where we when we replace square root n with things like cube root n or like square root n divided by log n or whatever. No, this is like square root n is the best we can do. And why does it? And why is it true? Well, one thing is that a squared minus 2b squared equals to 1. This thing has infinitely many solutions. And why is it so? Because of this theorem. Okay, so that's basically all the presentation I have. Thanks for listening.